ME 347, Example 11. An aircraft cruises at altitude of 10 kilometers on a standard day. A pitot tube is used to measure a stagnation pressure of 35 kilopascals. Calculate the speed of the aircraft and the Mach number, A assuming incompressible flow, and B accounting for compressible flow. For part C, calculate stagnation temperature, critical pressure, and critical temperature. For part D, show the ambient, stagnation, and critical states on a TS diagram. For this problem, we will assume steady flight and that the air is an ideal gas with constant specific heats at standard conditions for an altitude of 10 kilometers. Also, we will assume that the measured stagnation pressure is for flow brought to rest isentropically. Finally, we will assume, incorrectly, that the flow can be modeled as incompressible for part A. For part A, calculate the velocity and Mach number, assuming incompressible flow. From the isentropic flow relations lecture handout, your textbook, or starting from the Bernoulli equation, the relationship is given for the ratio of stagnation to static pressure as a function of the initial Mach number for an incompressible flow brought to rest isentropically. The stagnation pressure corresponds to the pressure measured using the pitot tube pointing directly into the upstream flow. The static pressure corresponds to the local pressure for still air. For the specified elevation of 10 kilometers, its value is 26.5 kilopascals and can be looked up in the U.S. Standard Atmosphere tables that are available in Appendix A of your textbook. Since we know the pressure ratio, we solve for the Mach number and plug in this ratio and the specific heats ratio, which is assumed to be about 1.4 for air, to get a Mach number of about 0.68. Next, to get the velocity from the Mach number, we first need to calculate the speed of sound. Again, assuming air is an ideal gas, we can use the simple relationship that the speed of sound is equal to the square root of the specific heats ratio times the gas constant for air times the absolute temperature. Again, we use the U.S. Standard Atmosphere to look up the temperature of 223.3 Kelvin at the specified elevation of 10 kilometers. Plugging in values, we get a speed of sound of 299.5 meters per second. Multiplying this by the Mach number obtained earlier, we get a velocity of 203 meters per second. For part B, we repeat the calculations for velocity and Mach number, but now we no longer assume the flow is incompressible. From the isentropic flow relations lecture handout or your textbook, the relationship is given for the ratio of stagnation to static pressure as a function of the initial Mach number, and this time for a compressible flow brought to rest isentropically. Similar to part A, we solve this equation for the Mach number, and from our known pressure ratio and K equals 1.4, we get a Mach number about 0.64, which is less than our value calculated, assuming incompressible flow. This is as expected because we are well above the cutoff Mach number of 0.3 for modeling a flow as incompressible. Next, to get the velocity, we can multiply our Mach number by the same speed of sound from part A to get 193 meters per second. Again, this is significantly different from our result for velocity for part A. Calculating the percent error, we get about 5%. Note that for typical engineering applications, a reasonable threshold for error below which we would reasonably neglect a term in an equation is about 1%. Thus, 5% error at a Mach number of about 0.64 is consistent with our threshold at a Mach number about 0.3 for including compressible effects. For part C, we calculate some of the reference states for this flow. Note that these do not always actually exist anywhere in our flow, but are calculated to define reference properties, for this case at the stagnation and critical conditions. First, for the stagnation temperature, and again using the isentropic flow relations handout, we calculate that for K equals 1.4, and from our calculated Mach number, that the ratio of the stagnation to static temperature is about 1.08. Using the U.S. Standard Atmosphere table one last time to look up a temperature of 223.3 Kelvin at an elevation of 10 kilometers, we get a stagnation temperature of 242 Kelvin. Note that this is the temperature the flow would have if brought to rest isentropically and is always higher than our original temperature, static temperature. This is because some of the kinetic energy goes into increasing the thermal energy of the fluid. Second, for the critical pressure, which corresponds to the pressure the flow would have if brought to the sonic velocity, we substitute in Mach number of 1 into the relationship from part B to get the relationship shown. Plugging in K equals 1.4, we get that the ratio of stagnation to critical pressure is 1.893. Finally, we calculate a critical pressure of 18.5 kilopascals. Third, for the critical temperature, we substitute in Mach number of 1 into the relationship from the beginning of part C to get the relationship shown. Plugging in K equals 1.4, we get a ratio of stagnation to critical temperature of 1.2. Finally, we calculate a critical temperature of 201 Kelvin. For part D, we plot all of these states on a TS diagram. First, since for all of these calculations we assumed isentropic flow, they all lie on a vertical line. Starting from our initial conditions at a pressure of 26.5 kilopascals and a temperature of 223 Kelvin, these represent the static conditions for the still air outside our aircraft cruising at a Mach number of 0.64 at an elevation of 10 kilometers. When some of the air stagnates on the tip of our pitot tube, the pressure rises to 35 kilopascals and the temperature rises to 242 Kelvin as the kinetic energy goes to zero. If instead of taking the air outside the aircraft and bringing it to rest, we speeded it up to Mach 1, then the pressure would drop to 18.5 kilopascals and the temperature would drop to 201 Kelvin as the kinetic energy of the air increases. As noted earlier, this is just a reference state for this flow and is not actually happening for this case.